Hi everyone, thanks for checking out this video. So this is going to be another lesson about the Gillespie algorithm, but this one's going to be a little bit different from the other ones because I previously made a couple of videos talking about using the Gillespie algorithm for simulating gene transcription. But I've gotten some messages from people commenting and like emailing me and stuff. People have questions about how to use the Gillespie algorithm for a system of chemical reactions. And I think this is something I didn't think about before, but when I was making the gene transcription videos, I was kind of just thinking about gene transcription, and it didn't occur to me that people are also like using the Gillespie algorithm um, a lot for like modeling chemical reactions, and people have like homework assignments about that and like other projects they're doing about that. And a lot of the time, the systems of chemical reactions can be like more complex and more difficult to figure out how to set up the Gillespie algorithm compared to just the gene transcription. So like the gene transcription is basically like a very simple, a very simple system to model. Um, and it was maybe like too simple of an example to use because yeah, I guess people are like watching the video and still not knowing exactly what to do for like a more complex system of chemical reactions. So I just thought I'd make this video, and I'll probably make one in MATLAB too. But this will be a Python video about how to use the Gillespie algorithm for a somewhat complex system of chemical reactions. So that's what this video is going to be about. So yeah, let's get started. So this is just something that I made up, but I made this up to be kind of somewhat realistic to like actual assignment questions I've seen in like actual chemical reaction systems that people have been like asking about how to model. But this is just like a hypothetical system of chemical reactions. So let's say we have four chemicals just called A, B, C, and D. These will be our four chemicals. And we're going to think about what happens when we mix these up. And two reactions can occur. So again, I just made these up because to be honest, I don't really have like any chemistry background, but I'm just making these up for the sake of like talking about modeling. So the first reaction that can occur is that we have chemical A and chemical B. When they like bump into each other or whatever, a reaction happens where the chemical A and chemical B are transformed into two units of chemical C. So we have A and B like bumping into each other or whatever, and then it becomes, instead of one A and one B, it's transformed into two units of chemical C. So that'll be the first reaction we think about. And then the second reaction is going to be if we have two units of chemical B and one unit of chemical C, and they all bump into each other or whatever, then they all become one unit of chemical D. So again, just like hypothetical reaction, I just like made this up, but it's like somewhat similar to actual systems people have been like asking me about how to model. So let's just say we're given this description of a chemical reaction system, and we're also given the ODEs for it, because again, this is kind of like when people have been like asking about what to model. A lot of times they're also given the ODE system. So yeah, we have the ODE for each chemical, and so if we're given these two things, the description of the reactions as well as the ODEs, the goal is to put together this table here, because once we can put together this table with the reactions and propensities, once we put this together, it'll be like super easy to write the code to actually run the simulation. So once we just get this table all set up, it'll be, yeah, super easy to do the simulation. But also, quick note about terminology. So in my previous videos, I've been calling this table the events and rates table because I was thinking of the events as being like either a gene, either like an mRNA is transcribed or it's broken down, and those are the two events. And then I was listing the rates, as in like the rate that each event was happening per unit of time. So I called it the events and rates table. But I noticed that in terms of like simulating chemical systems, people put together the same exact table, like mathematically speaking, but instead of calling it the events and rates table, they call it the reaction and propensity table. And so I'm using that terminology here just to keep it consistent with like most of the literature, on like Gillespie simulation for chemical reactions. So just what I was calling before events and rates, I'm just here calling reactions and propensities. But just yeah, it's the same thing. I'm just trying to keep the terminology consistent with what other people modeling the chemical reactions, what terminology they're using. But yeah, so reactions and propensities. But okay, so like I said, we just need to, like, given this information here, we need to put together this table. And then once we can just put together this table, it'll be super easy to write the code for it. But okay, so let's just pretend that we're not given the table, and we need to just think about how to fill in this table. So let's talk about just filling in the reaction side of it first. So how do we fill in the reaction side of this table? Well, we have two reactions, so we know there's going to be 2 rows in this table, because yeah, like 1 row per reaction. And we need to just think about, with each reaction, like what's getting updated and how's it getting updated, if we're keeping track of all the different levels of all the chemicals. So with our first reaction here, let's just say the first row in the table will be this first reaction. So we need to just write down what all is getting updated and how much is being updated by. Okay? So the first reaction, A and B are like bumping into each other or whatever and being transformed into 2 units of C. So we need to update all of our levels of the chemicals by having A go down by 1, B go down by 1, and then C go up by 2. So does that make sense to you guys? Because it's just basically whenever this reaction happens, we can think of it like we're losing 1A, we're losing 1B, and we're gaining 2C. So does that make sense to you guys? That's just why I wrote it like this. Like A is just going to the previous value of A minus 1, B is going to the previous value of B minus 1, and then C is going to the previous value of C plus 2. So that's just how I'm just getting that right from this picture here. We haven't even need to use the ODEs yet at all. Just right from this picture, I just know that that's what's happening when this reaction's happening. Just we're losing 1A, losing 1B, and we're gaining 2 C's. So that's just why I wrote it like that. And then so let's talk about the second reaction then. So what's happening with the second reaction? So when this reaction happens, 2 B's and a C all bump into each other or whatever, and it results in 1 D being formed. So what's happening here in terms of the levels of all of the chemicals is we have B going down by 2, C going down by 1, and then D going up by 1. Because remember, we're losing 2 B's, and we're also losing a C, and we're gaining a D. So that's how all the levels are going to be updated when this second reaction occurs. Okay, so I hope you guys are still following me. So that's just how we write down the reaction column for both of the possible reactions. Okay, so now let's talk about propensity. And remember, this is what I was calling the rates before in my previous videos, because it is the rate that the reaction is happening per unit of time. But I'm just calling it propensity here, just because that's what it's called in a lot of the literature, like modeling chemical reaction systems. But it's just the same thing as the rate column I was talking about in previous videos. So to get these propensities, we need to look at our ODEs, right? Right. So let's just say that we're just given this ODE system. We need to just find out what in here, what to put in the propensity column. So we can kind of, sorry, I'm just thinking about how to explain this in a clear way. So if you guys watched my previous videos, we just saw that with the ODEs, you could just take the term in the ODE and put it right in the rate column, because that would give you the rate that the reaction was happening per unit of time. We can basically do that here too, but we just have to pay attention, okay? So we can see like A, we have this term here. It's just A is just being it's just decreasing by this term here. Negative K1 times A times B. So this corresponds to the rate that this reaction is happening per unit of time, right? You guys following me there? Because that's just the relationship between like our graphical representation and the ODE. Like this reaction is happening per unit of time at rate negative K sub 1 times A times B. And then you might be, like, it seems maybe confusing at first because you see over here, like C, we can see it's going up by just the positive version of that rate times 2. That's just because we're getting 2 C's here. So that doesn't mean that the reaction is happening, it's not happening twice as fast per unit of time. It just means it's just multiplied by 2 because we're getting 2 units of C. But the rate that this reaction is happening per unit of time is this term here, negative K sub 1 times A times B. We can see it here in B too. I mean, with the ODE for B, we have to account for both reactions because it's decreasing by the amount that's being lost in this first reaction as well as the amount being lost in the second reaction. So that's why we have 2 terms here in B. And then with C, we have a positive term to account for however much it's increasing because of this first reaction. And we also have a negative term to account for however much it's decreasing because of the second reaction. And then D, we just have the positive term talking about how much it's increasing when the second reaction is happening. But here in the propensities table, we just basically want to write down the rate that the reaction is happening per unit of time. And we can just get those just by kind of intuitively thinking about what they are based on the ODEs. Another important thing is that whatever we're putting in the propensity column should be positive, because I know that this is negative here, but that's just to account for A decreasing by something, you know what I mean? But when we think about the rate that the reaction is happening per unit of time, we want it to be positive. So if we see a negative term here, it's just going to be the absolute value of it. Okay, I hope that explanation made sense. I know, even just kind of listening to myself, that maybe it didn't make sense entirely, but yeah, it's this part's kind of hard to explain. Yeah, I wish I could think of like a more intuitive explanation, but I would just say, like, to get the propensities, just look at the ODEs and try to see what are the rates that these reactions are happening per unit of time, and just take those terms and just put them in the propensity column for the appropriate rate. So this here is the rate for the second reaction. It's K sub 2 times B squared times C. Remember, the B squared is because this requires 2 B's to happen. Right, and in the B ODE, it's multiplied by 2 because we're losing 2 B's. But yeah, the B squared is just because it requires 2 B's to happen, and then that's how much also D is increasing by. So we just take this term here and put it in the propensity column over here. So I hope that made sense. If it's not clear, like, please leave a comment and I'll try to explain like any confusion. I know even just trying to explain it, it's kind of tough to explain. But I hope it made sense, and I hope you guys have like some intuitive sense for it. But yeah, so these are just the propensities are just the rates that these reactions are happening at per unit of time. Yeah. Okay. I hope you guys are still following me. But again, if anyone is lost, like please leave a comment and I'll try to further explain. But at this point, I'll just assume that you guys are still on the same page as me. So once we have this table put together, that's really the hard part. The hard part is just putting together this table. Once we have this table, writing the code is actually pretty easy. So now I'm going to talk about how to actually write the code now. Okay. So the first thing I do, like usual, is just import all of the libraries I'm going to be using, and then so after that, I'm going to just define the arrays that I'm going to be using to store the values in for each chemical. So we're going to have an A array that's going to be started off with just the initial condition, the first value that we're going to be using for A, which will be 100. And you guys can start off with, you can really start off with any positive value. Just make sure you're not starting it at 0, because something to notice is if you start any of these off at 0, like they're not going to be producing new ones from anywhere. Just for this reaction that I'm using, you have to start off with some positive number, or else it won't be getting produced from anywhere. So you have to start off with something positive. So I'm just starting with 100. You guys can start with whatever you want to start with. Also start off B at 100. Same with C and D. And like I usually tell you guys, with the Gillespie simulation, it's just we're gonna have an array for each thing we're keeping track of, and every time the simulation iterates, we're going to be appending to this array. So we're going to be appending like the value of it at each iteration of the simulation, and that's how the simulation is going to occur, is just like appending to these arrays. By the way, I mean, when I'm making this video, I'm kind of assuming you guys have like already watched my other Gillespie simulation videos. But if anyone hasn't seen those, I'll link to those in the comments if you want to see like a introduction to the Gillespie algorithm and also like a simpler introduction in Python for a simpler system to model. But at this point, I'm kind of assuming that you guys have already seen those videos. So I might go like kind of fast paced. But if you're feeling behind or you want like a simpler example or a more basic introduction, I'll link to the previous videos I made on those too. And then the next array we're going to be using is the time array. So we're going to start off the time at 0, and it's just basically all these arrays here. Every time the simulation iterates and a reaction occurs, we're going to be appending to all these to update the values to whatever the values will be after that simulation happens, including with also the time array too. Okay. So then we're going to have an endpoint. I just call tEnd end at 10. And then we need 2 parameters. So we need k1 and k2. Okay. So I'll just make k1 0.3 for now, and k2 will be 0.01. Like I always say, like I encourage you guys to like change these around, play around with different values, like try out different parameters and initial conditions and stuff, but I'll just keep it like this for now. Okay. So the next thing to do is we're going to have, like usual, our actual simulation is going to occur within a while loop. So we're going to say while the most recent value of t is less than tEnd, we're going to do our simulation. So this is just saying like while we haven't hit tEnd yet, while our most recent t is still less than our end t, we're going to keep iterating through this simulation. Okay, so the first thing we're going to do is put all of our propensities into an array. I'm just going to call it props for short. I call this the rates array in my previous videos, but I'm just trying to, for this one, keep with the chemistry terminology. So I'm calling it propensities here, but it's the same thing as the rates array in previous videos. So we have our first propensity is this one here, k1 times a times b. And remember, for a, we want the most recent value of it. So a to the index -1. This is our most recent value of whatever a is. Because remember, we're going to be keeping track of all these chemicals in these arrays by appending to the array every time our system is updated. So we want our most recent value, which is a to the index -1, and then times the most recent value of b, which we get the same way, just putting the array to the negative first index. So that's the first propensity. Second propensity is going to be, excuse me, k2 times most recent b squared, because remember it requires two b's to do the second reaction. It takes two b's. Times most recent c, right? Yeah, okay. So that's our propensity array. And then we want to compute the propensity sum. Because remember, these are going to be getting updated like each iteration as the values of things change. It'll actually be like different propensities. They'll be updated as the levels of the chemicals are changing. So the sum could actually be different, each iteration. So we want to compute each iteration. I'm going to call it prop sum. It's going to be the sum of the propensities. Again, I called this rate sum before, but this video just keeping the chemical reaction terminology. I'm just calling it propensities here. So call that prop sum. And then, okay, this part's important because, okay, we need to check if the prop sum is 0. And if it's 0, we want to just break out of the while loop. Because if it goes to 0, then we can't do the rest of this while loop, or else we're going to get a divide by 0 error that you guys are going to see in a second. But we're going to say if prop sum equals 0, break. And you guys are going to see why that is in a second. But yeah, which is if the prop sum is 0, we're just going to end the simulation and return all the results then, and just break out of the while loop, and whatever levels we have, that's just going to be where it ends. And you guys are going to see why in a second. Yeah. So just as a refresher, and again, if this is new to you guys, I encourage you to check out my introductory video on the Gillespie algorithm. But with the Gillespie algorithm, just to remind you guys, it has 2 steps. So the first step is to choose the time that the next reaction will occur. And it should be a random choice, but a random choice that makes sense. So we randomly choose the time that the next reaction will occur, and then we randomly choose which reaction that will be. So those are the 2 steps that we do each iteration. So our first step here is just choosing the time point when the next reaction will occur. So the way we do that is by defining some variable tau, which is going to be a random draw from an exponential distribution. So we do that with numpy.random.exponential. Sorry, forgetting the spelling for a second there. And then we want the mean of this, called the scale, to be 1 over the prop sum. So yeah, so we're picking this random variable tau, which will be a random draw from an exponential distribution with mean 1 over the sum of the propensities. And if this is new to you guys, I encourage you to check out my previous intro video on the Gillespie algorithm, which I'll link to. But at this point, kind of assuming that you guys are following me here. So then once we have this tau, we're going to update our t array by appending whatever the latest value of t is plus tau. This is how we pick randomly the time point that the next reaction will occur, is just by having this random draw tau from this exponential distribution, and then updating the next time point to be the previous time point plus tau. So that's basically tau is however much the time is being incremented. You know what I mean? So hope you guys are following me there. But yes, that's how we update our t array. And then so once we pick the time point of the next reaction, we need to pick which reaction will be happening. Okay, so again, I'm going to go through this part kind of fast, kind of assuming you guys have watched my previous videos. But so the way we do this is we take another random number. This one's going to be a uniform random number. between 0 and 1. So just some random decimal between 0 and 1. And then I'm actually going to, I'm going to copy and paste this part. Just a little bit of laziness just because I'm just kind of being lazy. Don't feel like typing all of it. I'm going to copy and paste this part and then explain it. So basically, this is how we pick, once we pick the time point of the next reaction, this is how we pick which reaction it's going to be. So basically, we multiply this random decimal by our sum of the propensities, and we check if it's less than the first propensity, less than or equal to. And if this is true, then we know that we've picked the first reaction. And then if that's false, then we know that we've picked the second reaction. So really in this case, I could have just put else here. I could have just put else because there's only two reactions, so we know if it's not the first, then it must be the second. But instead of putting else, I actually just wrote out the full elif statement because I wanted to show you guys what it would be if we had like a more complicated system with like more than two reactions. So I could have just put else here, assuming that if it's not the first reaction, it must be the second. But I just wrote out the whole thing, and the whole thing is like if this first condition is false, then we check if this product of the random number times the sum of the propensities, if it's greater than the current value of the first propensity, but also less than the sum of the first propensity and second propensity. And I wrote this whole thing out because if we had more than two more than two reactions, we could just keep basically doing this for each reaction that we're checking. So for every reaction we want to check, we just want to check if this random product of the random number and the sum of the propensities, if this is greater than the cumulative sum of all of the propensities for the previous reactions, but if it's also less than or equal to the sum of the propensities for all of the previous reactions, but also this new reaction we're checking. So basically just we have this random product and we want to check and see like, okay, is it less than or equal to this propensity? And if yes, then we pick this reaction to happen. And if not, we say, okay, well then is it less than or equal to the sum of these propensities? And if yes, then we pick this reaction to happen. And if no, let's say there were more reactions, we'd say, okay, is it less than or equal to the sum of all three propensities here, assuming we had a third reaction. And if that was true, then we'd pick the third reaction. So just kind of like cumulatively, sorry, I can't say that word, but you know what I mean. All of them, just summing them up, and just checking where this random product falls. And when the condition is true, then we know that we've picked that reaction to occur. And this is just a way of like randomly picking which reaction will happen in a way that makes sense based on the propensities of the reactions. We can also, basically another way to think of this is that we're just taking a random draw between all of the possible reactions where we weight the probabilities accordingly. So the probability of this reaction happening is just this propensity over the sum of all the propensities, and the probability of the second reaction happening is the propensity of the second reaction over the probability of the sum of all of the propensities. You know what I mean? So to get the probability of this reaction happening at any time point, I should word this more carefully. To get once we pick the time point of the next reaction, to get the probability of that reaction being picked as the first reaction, it's just the first reaction's propensity over the sum of all the propensities. And to get the second, the probability of that reaction being the second reaction, it's just the second reaction's propensity over the sum of all the propensities. But just the way we write that into code to actually do the checks is writing it like this. Okay, so this is how we check which reaction is going to be the reaction that occurs. Sorry, I got to take a deep breath after explaining that. But yeah, so now we just need to think about how to update everything. So we need to update all of our, whenever a reaction happens in the while loop, we need to just update all of our levels of all the chemicals. And also, don't forget also to update the ones that aren't being changed, because we need to update those too with whatever the current state is, even if the state isn't changing. But yeah, so the way we update if reaction 1 happens is it just whatever. Remember when we wrote down just this stuff in our reaction column? This is just telling us how to update everything if if the first reaction happens. So A is whatever the most recent value of A was -1. We're updating by appending to the A array with that value, the latest value of A -1. And then we update B by appending to the B array with whatever the latest value of B is -1. We update C by appending the latest value of C +2, because remember, we're getting 2 C's here, and we also wrote that down here in the table. So it's +2 there. And then D isn't changing, but we still need to update it just to keep track of what, because we want a measurement of D at each time point that we're recording. So even though D is not changing, we're still just going to update to record that it's still just whatever the latest value of D was. It's still that same value. So that's why we're just updating with whatever the latest value was, just saying, okay, it's still that same value. Okay. And then if the second reaction is picked, A isn't involved, so A is going to be whatever, just the same value. B is decreasing by 1, because remember, we're losing 2 B's here, which we wrote down in the table like that. So, I mean, sorry. Did I say B is decreasing by 1? I meant to say B is decreasing by 2 there. Yeah, so B is decreasing by 2. C is decreasing by 1, because remember, we're losing 1 C, which we also wrote down in the table. We wrote down the table here. C is decreasing by 1. And then D is increasing by 1, because we're gaining 1 D. Okay. So, yeah. So as this while loop iterates, so remember, the while loop is going to be happening until it reaches T end, or until the prop sum ends up equaling 0, because if the prop sum equals 0, we're going to get a divide by 0 error here, because it just means that when the prop sum is 0, there's not going to be any more reactions happening, and if we try to take a random draw here, we're going to get a divide by 0 error. So we're just checking if the prop sum is 0, and if it is, we're just breaking out of the while loop and ending the simulation, which I think is actually what's going to end up happening, by the way. But if not, if it never reaches 0, then we're just ending at T end. But okay, so yeah, this here is basically the whole simulation. So the next part is just going to be plotting. Just want to plot the results. So again, sorry, I'm going to be a little bit lazy here. I'm just going to copy and paste the plotting part, but I'll also explain it too. But just copy and paste the plotting part. So just each trajectory, we want to plot a line for that trajectory. So just the first one is just plotting the T array and our A array and labeling it A. And then we plot the T array and our B array, and then T and C and T and D. And then this is just how we make the legend, which will show the labels for each of the trajectories. And then we're going to label the x-axis time, the y-axis is the abundance of the chemical types. And then and then lastly plt.show, right? Okay. So I hope this works. See if it works or not. Oh yeah, sorry, I forgot. Let's give the terminal ready. Okay, so we got some results. We got some results here. Yeah, so and I'll actually just run it again. I'll show you guys how it like varies a little bit each time we run it, but not by much. Yes, that's after running it again. It looks kind of the same. This seems to be like approaching the same steady states, But since it's stochastic, it's like a little bit different each time. Maybe I'll even run it a third time, just to emphasize this point. How it'll be like a little bit different each time, but it shouldn't be like so different in this case. But yeah, a little bit different each time. Not too different, but you can see like the randomness part of it. Okay, so now I have another question for you guys. So how do we know if we're getting these results? How do we actually know if this is correct? You know what I mean? How do we check our work and know that we did it correctly? So the next thing I'm going to be showing you guys, just to finish off this video, just something important because there's a lot of steps to this. So it's like, how do we know we actually got this right? And how do we know we're actually seeing the results we should be seeing? So I'm going to show you guys how to do the Gillespie algorithm, what I call just the sanity check. Like just check and see if we know what we're doing, see if we did everything properly. Just see if the trajectories are actually what we're supposed to be seeing. So the way we do the sanity check is just to plot the stochastic results alongside the ODE plot results. So I'm going to show you guys how to do that now. Just if you guys have seen my previous videos, I've talked about also how to plot like ODEs in Python. So I'm going to go through this like kind of fast. Kind of fast. Because I don't want this video to be like too long. Actually, I might even, sorry for being lazy again, but I might even just copy and paste in like all of this, and I'll just walk you guys through it and explain each part. But yeah, so this is just going to be, I'll actually just comment here. ODE plot sanity check. So this is just going to be the part where we just plot the deterministic ODE results. We're going to plot this alongside the Gillespie results and just check and make sure that it looks like we're getting it right. You know what I mean? So basically, we wouldn't just, because we know that the ODEs are going to be, like we're assuming that we were given the ODEs for like the homework assignment or the project or whatever we're doing. We're going to say that we know deterministically how to model the system. We have some deterministic model, and we're trying to make a stochastic model. So to check and see if we match, what we're going to do is just plot the ODEs alongside the stochastic results. So I'll show you guys how to do that. So I just copied and pasted this in. I'm just gonna sorry for being kind of lazy. I just don't want this video to be like too long. But I'm just gonna go through each part of this chunk of code here. So first of all, what we need is just a t end for the ODEs. So I call this new t end here. This is just going to be because remember the Gillespie simulation got broken off before the actual like absolute t end. It got broken off when prop sum hit 0. If you're paying attention in the plot, you can actually see that it didn't go all the way until time 10. It broke off early. So we're going to say that the t end for the ODEs is just going to be whatever our last value was in the Gillespie t array. That's going to be our new t end. And then our initial conditions, we're just going to be, make a comment here, just this is the initial conditions for A, B, C, and D. I just made them all 100, but again, like I encourage you guys to, to try them out with different initial conditions, but I just kept them the same as up here. But just remember, if you're doing the sanity check, just make sure you have the same initial conditions for both the Gillespie simulation as well as the ODEs. Just make sure you're keeping them all the same across both simulations. So then we're going to say our ODE t array, just going to make a new array also called t, just going to overwrite the old t variable. Because we've already plotted it at this point in the code, so it's going to overwrite it. So the new t variable is just going to be this array starting at time 0 and going to time new t end, whatever our just last value was that we reached in the Gillespie simulation, last value of t, and then we're going to want 1,000 time points just in that space of time. And then params k1, k2, just put those in an array. It's going to be just, the same. We've already defined them up here. And I'm just keeping the same values as before. And then, so we got our initial conditions, our time array, our params. And then for writing the simulation, I'm going to go through this kind of fast because I'm kind of, at this point, assuming that you guys have watched my, more introductory videos. But if not, I'll link to them, how to write all of this, ODE simulation function. I'll link to like the more introductory videos I did on them. But basically, we just want to locally define all of our chemical levels. So we're just defining A as whatever is in this variables array we're going to pass in. This will be the first initial condition we're going to pass in as this variables array, and just the first value of it is going to be A. Second item in this array is going to be B. C is the third item, and D is the fourth item. So we just define all these levels just locally in this function. And by the way, we're making this function just as something that's going to be passed into the actual ODE solver. So that's why we have to make this function. Again, if this is new to you guys, I encourage you to check out my previous introductory videos. So we just define these locally. We want to also define the parameters locally. Just defining K1 is just the first item in this parameters array, and K2 is the second item in the parameters array. And then, so once we've defined everything locally, just the next part is just to write down all the actual ODEs, all the actual equations. So we just write them down just as they are, you know what I mean? So dA, dt, just make it a new variable and just write down exactly what's here. Negative K1 times A times B. Just do that for all of the equations we have here. Yeah, just write them down exactly like they are. And then we want to put all these, like, we just want to return all of these ODE variables we've made. We just want to return these in an array, which will be our output. So yeah, we just need to make that function. I just call it the sim function that's going to be passed into the ODE solver. And then so the last part here is we have our ODE function, the initial condition array, the time point array, and our params array. We just want to use this ODEInt function that we're getting from SciPy, scipy.integrate. We're importing the ODEInt function to actually like integrate this whole thing. And just this is just going to be the ODE solver we're going to be using. We just call this function, and we just pass in the name of our ODE function that we defined. Sim, I called it. Just pass in the name, pass in the initial condition array, pass in the time point array, and then args equals parentheses params comma. Just a bit of weird syntax there, but that's just how we pass in the parameter values. Okay, so then the next part is plotting. So we're getting this output matrix Y. So Y is going to have it's going to have a row for every time point and a column for every variable. So there's going to be 4 columns and a row for each for the value of that variable at each time point. So this is going to be, I'll just make it clear what we're actually plotting here. The first one is just all of our values of A, because remember that's the first our first variable is just called A. So we want to just plot our time points and then the value of A, which is the first column at each time point. This is just the syntax for plotting all of our A values here, and then B, and then same thing for C, and then D. Again, sorry if I went through this kind of fast. I'm kind of assuming you guys have like watched the previous videos on Python for ODE simulation, but if not, I'll link to those. But kind of went through this fast here because really what I want to show you guys is just what it looks like when you plot the ODEs at the same time as the Gillespie results. Just to do this kind of like sanity check, just to make sure we're getting the Gillespie simulation right. So yeah, I'll just show you guys that now. And yeah, just make sure we commented out the previous plt.show. And yeah, hopefully you guys will see what I'm talking about. Yeah. Okay, so you guys can see like the bumpy lines. The bumpy lines are stochastic simulation results. You can see them kind of here and here. And then the smooth lines are the results of the ODE system simulation that we plotted. So, and we know that we got the Gillespie simulation right, and this is the important part. This is the actual sanity check here. We know that we got it right, and our simulation is valid because we can see that the Gillespie simulation results for each variable are approaching, like in the long run, they're approaching the steady states that we see in the ODE simulation. So does that make sense, you guys? So for each one, we see that it's not exactly the same as the smooth line, and we wouldn't expect it to be because, you know, it's stochastic, so we expect it to be kind of bumpy. But we see that even though it's bumpy, and even though it's especially bumpy in the beginning, we know that it's a valid simulation because we know that if we were to run the simulation like a lot of times, it would approach, you know, it would approach the same results as is in the ODE simulation. So does that make sense, you guys? I hope you guys are following. If there are any questions, like, please leave a comment. But yeah, and I'll try to explain further. But I mean, I hope I explained it a way that made sense. But yeah, any questions, please just comment, and I'll try to answer any confusion that anyone has. But yes, that's going to be it for today's video. Just want to say, like, thank you to you guys for watching. Any questions, leave a comment. Also, just something cool. I think it's been cool. People have been like reaching out to me, like asking for help and stuff. One thing I think is really cool is I've been seeing like how people are like watching these videos like all over the world. Like I had someone like, you know, reach out to me from the Philippines asking for help. Someone else from India, someone else from Africa. So I think it's super cool that people are like watching my videos from like all over the planet. I think that's like totally awesome. So yeah, I mean, maybe if you guys, I'll just say, like, if you guys are watching this in a country like outside of the US, maybe you want to like leave a comment and just like, you know, say where you're watching from. Just because I think it's cool, you know, seeing where people are watching these videos. I mean, I think it's cool people are watching these all over the place. It makes me feel good, at least, that, you know, people are finding these helpful like all throughout the world. I think it's awesome. But yeah, so just thank you guys for watching. And just any questions, let me know. And yeah, just see you next time.